I'll record that class. I'll record that class now. Now, in our last class, let me share what we are going to discuss today. Let me share what we are going to discuss. This is what we are going to discuss for today. This is exactly what we are going to discuss. Last time, we had a coil. We had a resistance wire, or what we call, yes, a heater, an electric heater. And then we said, when that coil is connected to electric current, the electric current is converted into heat energy in the coil. And so the coil gets warmer. And if it is subjected to very high currents, it becomes even red hot. It becomes red hot. And so, when does that heat energy come from? Where does the heat energy come from? We say that heat energy comes from when we have we have the battery pumping or doing the work of moving electrons in that coil. And we say the work needed in moving the electrons in that resistance wire is much higher than the work needed in moving the electrons in the other connecting wires. So you realize that the coil becomes very hot compared to the other part of the circuit. Where does the heat energy come from? It comes from that work energy, and that work of pumping electrons around the circuit. So when you are pumping those electrons in that resistance wire, then you have the resistance wire becoming very warm. If I can show you, last time we had the effect we discussed the effect of time. And if you can refer clearly from that audio that we have sent, I have clearly explained the effect of time. And I also clearly explained the effect of what? I also explained the effect of current. And we saw clearly that when you supply current to the coil or the resistance wire for a very long time, then you have the resistance wire becoming very hot, very warm. So the more the time that the connecting wire is connected to current, then the more the coil becomes hot. And when the coil becomes hot, you expect that the paraffin gets heated. And when the paraffin gets heated, the temperature of paraffin increases. It changes from an original value to another value. So we saw the effect of time, and we saw the effect of current. Now, number 3 for today, I think you can see my highlighting. Today we are going to see the effect of resistance. And how are we going to vary the resistance of that wire or that coil or that electric heater? To vary the resistance, we are going to vary the length of the coil. Now in physics, you must know that when you vary the length of a coil, then you will be varying the resistance of the wire. The longer the wire, the more the resistance. You see, you must be getting it clearly. The longer the wire, the more the resistance. So, can we have somebody reading for us what you can see on your screen for the effect of resistance? It's the last one, because we have the effect of time. Next, we have the effect of current, which we explained, and the effect of resistance. If I can recap clearly, I can remind you, for the effect of current, we say now you have what? You take a current of around 0.2 ampere. Around you get that current, you vary using the rheostat. When you get a current of 0.2 ampere, you take the initial temperature of paraffin. And then you wait for 2 minutes, you get the final temperature. And now, if you get the final temperature minus the initial temperature, you are able to get the change in temperature. That is now for the current of 0.2 ampere. Vary the current to 0.4 ampere. And again, get initial temperature of paraffin and final temperature of paraffin. Then get the change. Go to another current. You will realize that the more the current, the more the change in temperature. A current of 1 ampere causes a bigger change in temperature than a current of what? Than a current of 0.2 ampere. So the more the current, the more the change in temperature. And also we say that the more the time the coil is connected to current, the more the change in temperature of paraffin. We expect that the paraffin is being heated by what? We heat the paraffin using the coil. And where does the coil get that heat energy? It gets heat from the flow of electrons. The electrical energy from the battery. The battery. That motion of that movement of electrons, that work needed to move the electrons in that coil is what is converted into heat energy. And that heat energy is used to heat the water. The coil is used to heat the paraffin. Now, for the effect of resistance, can we have somebody reading for us? Effect of resistance, what you can see on the screen. Let us have somebody reading so that now we can move on together. Somebody can read for us. Nixon?
Set current.
Nixon?
Effect of resistance. Set current to a certain value. This value of current will remain constant all through.
Pause kidogo.
Using a...
So you see hapo, we are saying, here we are looking at the effect of resistance. So we are going to keep the current constant. Are we together? So here we are not going to vary current. In this case, we are going to vary the resistance. So can you read on next?
Using a short coil or resistance wire, get the temperature change caused by this coil on paraffin for 2 minutes.
Good. You use a very short coil and you get the temperature change caused by this coil on paraffin for 2 minutes. That is, nichukue coil. Hiyo coil, hiyo resistance wire, niweke kwa paraffin. Then I start my stopwatch. I'm imagining now the switch is on. Then I get the initial temperature from the time I started the stopwatch and the final temperature after 2 minutes. Nione, for that coil, that short coil, what is the change in temperature in 2 minutes? What is the change in temperature of paraffin? Then, can you read on?
Repeat point 2 above using other resistance wires of different lengths. Repeat point 2 above using other resistance wires of different lengths and for each
resistance. Wire. For each resistance wire.
For each resistance wire, determine the temperature change it causes for 2 minutes.
Good. Now, so you started with a coil. Same hapa, you started with a coil of 20 centimeters. See there. Ukaenda ukatumia ya 30. Ukaenda ukatumia ya 40. Ukaenda ukatumia ya 50. And for every coil you do what? For every coil, check what is the temperature change it causes. Kwa kila coil, Ukiweka kwa paraffin, start the stopwatch, close the switch, wait for 2 minutes, get the final temperature. You will realize that the longer the coil, the more the change in temperature. If you have a very long coil, then it has got very high resistance. If you have got a very long coil, because it has got very high resistance, then the work needed to move the electrons in that coil is equally very high. Yes, the work needed to move electrons in that coil is equally very high. If the coil is very long, you will require to do a lot of work. The battery will require to do a lot of work. Remember, the battery pumps electrons around the circuit. So as the battery pumps the electrons around the circuit, it will do a lot of work, or the work needed for it to do that is much higher if you have a very long coil. And so if you have a very long coil, then you expect the heat energy will be very high, because the work done that you have done is also very high. So the temperature change will be very high. So the longer the coil, the more the heat energy it supplies to paraffin. So you see now, this is the effect of resistance now. So here now, let us come to our analysis. We have talked about 3 effects. Lazima uende uangalie effect of time, vile tulisema, effect of current, vile tulisema, na effect of resistance. And they are very clear. If we come here, we shall have 3 graphs. Look at those 3 graphs. We shall have one graph for temperature versus time. We shall have another graph for temperature versus current squared. The square of current. This one is the square of current. Let me space here. It is temperature versus the square of current. Like that. Temperature change. This small triangle that you can see there, it means temperature change. So it's a temperature change. And then you have got another one, another third graph for temperature change versus resistance, R. All these graphs will be straight lines through the origin. Look at my graph. The temperature change versus time, it is a straight line through the origin. A straight line means what? As time increases, the change in temperature also increases.
Directly proportional.
Yes?
Directly proportional.
Yes, good. Directly proportionality. That is what we mean by directly proportionality. I think that one is very good. Very good. The change in temperature. Yani, ukichukua for 2 minutes, the temperature change on paraffin, itakuwa kidogo than the temperature change if you do it for 6 minutes. For 6 minutes, paraffin itagain temperature sana. And so the temperature change will be very high. Now let's come to the next graph. It is a graph of temperature change versus resistance. Ndio tumeona just, is the one that we have just seen. Tumeona nini? What have we said, by the way? Somebody can tell us what we have said. And we have somebody reminding us what we have said for the resistance. Somewhere. For resistance, can we have somebody? Nixon?
We have said that the longer the wire, the higher the resistance.
Good.
And resistance is directly proportional to temperature.
To temperature change, sindio? Because tukasema nini? Let me use the loosest language as possible. Kama coil iko very long, you will require, the battery will do a lot of work to pump the electrons in that coil. And the more the work it does, the more the heat energy. Are we together? The more the heat energy. So again, that graph is a straight line through the origin. That's directly proportional. If the resistance increases, temperature change also increases. And how do you vary the resistance? By varying what? Somebody? How do you vary the resistance of the wire? How do you vary the resistance? Patrick Muturi? By varying the length.
Yes, the length.
Yes.
You're varying the length of the wire.
By varying the length of the wire. That is very good. Now, look at that other graph. A graph of temperature versus current squared. Can you see it? Temperature versus the square of current. Okay, tuliona nini for current? Tuliona, the more the current you use, the more the temperature change. The more the current you use, the more the temperature change. So inamaanisha, the square of temperature will also be increasing. So if current is increasing, the square of temperature, no, the square of current, the more the current, the more the temperature change. So when current increases, then the square of current also increases. And the graph of temperature change versus current squared is also a straight line. Now we have these three equations. Look at them now. This one, the first one is here. It says what? Current is directly proportional to time. I think I can try to annotate here. I can try to annotate. I think I need to try to annotate here. I need to show you these things because they are very easy now. Now, the change in temperature like that is direct, the change in temperature. The change in temperature is directly proportional to time. The change in temperature is directly proportional to time. I think that one is it. It is here. And then again, the change in temperature is also directly proportional to the change in temperature is also directly proportional to a resistance. Directly proportionality means when one increases, the other one increases. So we have got those three equations. We have got those three equations now. Now, there is this thing that we call temperature. We have temperature now. I want to tell you about temperature. Let me first make this. Now, because we are talking about temperature, temperature is directly proportional to heat energy. If the temperature of our body increases, then the heat energy in it also increases. And so, the change in temperature, we are taking it to be the same as what? We are taking the change in temperature, this one, to be equal to the electrical energy supplied by the heater. So temperature, the more the temperature, the more the heat energy. And that heat energy, it is electrical energy supplied by heat. And so our equation comes now look like this. Now look at the way our equations now look like. Our equations now are like this one. We have changed, pale tuko na change in temperature now tumeweka. Where we had change in temperature now, we have now electrical energy. Ama heat energy supplied by the heater. So if you combine the three equations, heat energy is directly proportional to time. Heat energy is directly proportional to resistance. Heat energy is directly proportional to current squared. Now we have got this mega equation, this one here. I think you can see it here. This equation, this one. Look at this. It means heat energy will be directly proportional to the square of current, resistance, and time, like that. The square of current, resistance, and time, like that. Now look at it. And then now, we drop the sign of proportionality. If we drop this sign of proportionality, this one, we use now the equal sign, we have arrived at an equation here, a very beautiful one. This equation, it is the equation for the electrical energy supplied by the heater. So electrical energy supplied by the heater will be given by what? Current squared times resistance times time. The time when you are working out, wakati tutakuwa tunatumia this equation, ensure that your time is in seconds. In physics, we do not use time in minutes, pali popote. Even time in hours, we only use it when we are calculating the capacity of an accumulator. When we were in Form 1, tulikuwa tunafanya what we call capacity of an accumulator. I remember when we were doing the capacity of an accumulator, we used to use time in hours. Na ile ingine pale pengine huwa tunatumia time in hours, we shall see it in Form 4. Watu tutakuwa tunauza stima when we shall be doing what we call electrical. So we have this equation. Look at this equation. Electrical energy supplied by the heater equal to current squared times resistance times time. Now, I want you to recall. There is a recall here. Power is the rate of doing work. Or we say that power, the rate of doing work means what? Rate means divide by time. Rate of doing work. It is work divided by time. Or you can say power, it is work done per unit time. Power is work done divided by time. And here we come and make another remark here. Another very important remark here. That is this is an NB, this one. This one I can write it as an NB, a very important note going through. In this case, can somebody read this important note here? Can I have somebody reading this important note? Read that important note. Somebody, James?
In this case, the work done in moving electrons in the resistance wire is the same as the electrical energy supplied by the heater.
Good.
Thus,
Yes, now let me talk. Now here, that work done in moving electrons in the resistance wire, that one, it is the same as this thing, electrical energy supplied by the heater. And this electrical energy supplied by the heater is the one we were denoting with what? H dot E. And it is the same as what? I squared times what? Times resistance times
R.
I squared times resistance times time. So that now we come to this equation of ours, work done, instead of now saying work done, So work done is the same as heat energy, electrical energy. In physics, work done is analogous to energy supplied. For example, hapa, we are saying what? The work that you do, the work done in moving electrons in the resistance wire, it is the same as the electrical energy that will be supplied by that heat. Now, electrical energy tumesema, it is given by I squared RT. And so, now look at this equation. Power is equal to what? Look at this equation. Power. Now, our work done is the same as heat energy. And you see, our work done is the same as heat energy. And our work done is equal to what? I squared RT. So T and T will cancel. Look at T and T. They will cancel. And so we have gotten this equation. Power is equal to I squared. Power is equal to what? I squared R. I hope the equation is very clear up to that point. This one. Anybody who is not understanding this derivation, we have written that to Meandika. Let me try and write. Let me try and write these things for you again. Like let me show you. And now let me use this work. Let me use this one. Tumesema heat energy. Heat energy is the same as what? I here times R times what? Times R times T. See that? And this heat energy, this one, is the same as what? Is the same as work done. It is the same as work done in moving the electrons around the circuit, in moving the electrons in that resistance wire. It is the same as work done in pumping those electrons down that resistance wire. So again, that work done will be I squared R T. But now since tumesema power, tulisema power is equal to what? Work done all over time. Now you work done, this work done is the same as this heat energy. Okay, so you have what? You have I squared R T divided by T. And T cancel out with the T. Can you see that? Can you see that now? Am I clear to that point? Anybody with a question up to that point? Because this is what we are going to be using in calculation. This power. So we have got what now? Let me try here. So you have what? Power. I squared times the resistance. Look at that. Now tumepata power. Tumepata power. No, not really. Power. I have forgotten how to write letter P. I squared. Now I want somebody now. Now let us use Ohm's law. From Ohm's law, V is equal to what? I R. You remember this one? You remember this one? V is equal to IR. You remember it? Anybody who can remember?
Yes.
Yes, you remember
Yes.
it. No.
Yes.
I
Yes.
want us to do this. Nataka tufanye hivi. This power, this one. This power is equal to what? This one. I times I R. Can you see that? I times R. Can you see that? So what is this? What is this? What is this?
Yes.
What is this? This is V, Sindio. It is V. I think this one should be power, this one. This one should be power. Can you see that?
Yes.
Let me repeat it. Let me repeat it. Let me repeat it. I want it to be very clear. I want it to be very clear. I want it to be very clear. So this power is equal to I times I times R. You can see. But what is this? It is V.
Voltage.
So can we say that?
Yeah.
Can we clearly say what is happening? What is happening now? Are we staying together? I can see other things.
Yes.
Hey, now we are back. Sindio. Can we now say another equation for power? Can we say another equation for power? P can also be given by V times I. Do we have that?
Yes.
Yeah.
So this one has got P,
Yes.
I. Look at it now. We have that. And we have got this. Are you together?
Mm.
Can we have somebody else now? Can you work it out there? Can you substitute now for I, such that substitute for this I, this one. Let me show you. Let me show you now. Another equation. So we have not, so far we have P is equal to I squared R. And it is also equal to V I. Nataka sasa to substitute E I. From this Ohm's law, I is equal to what? I is equal to
V over R.
V over R. Good.
V over R.
Put this V all over R here. Here, put it there. Power becomes what? Power becomes
V squared
V
over R.
Squared
V
over
squared
R.
all over
R.
Sindio.
R.
Now we have 3 equations, Philip, and the other guys.
Yeah.
We have 3 equations now. We have got 3 equations. Let me show you now. Tuko na power equal to I squared power is equal to V I. Power is equal to V squared all over R. Sindio?
R.
R.
Sindio hizo? Those 3.
Mm.
Yes.
Then Once you multiply, the moment you multiply here by T, it becomes what? Heat energy supplied by the heater. Are you together? It becomes heat energy supplied by heater. Is it?
Anna.
If, for instance, now, let me show you now. Let me take a thing. For heat energy. For heat energy supplied by heater. For the heat energy supplied by the heater, we are going to have what? Let me show you now. The moment you multiply this equation, this one should not be here. It's going to confuse. The moment you get to this equation, you multiply here by T. Here, it becomes heat. So heat energy supplied by the heater and be given by what? I squared
RT.
T. Sindio? Ama, it can also be given by what? V I T. Is it? This one, the second one.
Yes.
Or heat energy supplied by that heater can also be V squared all over
R
times
T.
There are so many equations, Sindio?
Yes.
So this part here, in power E. This part here, this is power, Sindio? This part here, this is power, Sindio?
Yes.
So
yes.
can we say finally that heat energy is given by power times time.
Time.
Can we have that one?
Yes.
So we have got so many equations here. I can see 1, 2, 3, 4, 5, 6, 7. Can you see that?
Yes.
Yes.
Those equations will be visible to you in your audio, in your video, because we are going to share the video. Are we together?
Yes.
We are going to share the video.
Yes.
I hope I am. My recording is still on. I'm going to be sharing the video. You will take time to look at these things. Now I want to show you something else. I want us to remember something. Who can tell us the way we defined potential difference in Form 3? How did we define potential difference? Recall. Yes. Somebody recall definition of P&D between 2 points. Wakati tulisoma ile chapter ya current electricity. What was the definition? Somebody? Philip?
Potential difference. It is the energy required to move electrons in a circuit.
Required
to move electrons in a circuit or a wire.
In a circuit. That one is a very good trial, but there are some keywords. I want us to, instead of us to use energy, tutumie kitu inaitwa wa. It is the work needed to move. Remember, to move a unit charge from one point of the circuit
another
of the circuit to another. You remember this definition?
Yes.
The work needed to move a unit charge from one point of the circuit to the other. Alafu tukaenda hapo chini. You remember tulienda tukaandika P and D into brackets V. P and D tukaandika, which is denoted by V. Tukasema is equal to what?
Work done.
It was work done, sindio?
Over time.
Work done divided by
In joules.
Hapana, haikuwa hivyo. It work done to move a unit charge. How was it?
Divided by charge.
Yeah?
Divided by charge.
Divided by charge.
It was divided by Q.
Divided by charge moved.
Sindio?
Yes.
I want to show you whatever we have done is not very new. Are you together? Whatever we just done, Philip, is not very new. That's how to connect V. This one we knew is equal to work. We know that. Sindio?
Yes.
So, can we say work done is equal to multiplied by Q, Q times time? No, not
Times
time.
V.
Times V, sindio?
V.
And this work done, tumesema, it is the same as what? Heat energy.
The heat energy
is equal to Q V. Is it? But what is this Q from Form 1? This Q from Form 1. This Q from Form 1.
is charge.
Hapana.
IT.
In terms of a formula.
IT.
IT.
Oh, Q is equal.
Q is equals to IT.
So I get V I T. Sindio? I have still gotten the same equation, the one that we had for heat energy. Sindio? I've still gotten the same equation that we had for heat energy, but now following another formula. Sindio?
Yes.
Is it?
Yeah.
Yes, this one. This equation, this part is power. When you multiply power times time, you get heat energy supplied by the heater. I think for today's class, we can stop it at that point. And then next time, we shall continue. For you to understand these things, make sure you revisit them. You need to revisit these formulas. They are very easy. They are very beautiful. You are going to use them all through. I think the class has been good. Anybody with a question or something to say? There are some people who disappeared. We were at a point we were around 28. Now we are around 20. Anybody with a question? You can raise up your hand. Nixon, who is speaking? Raise up your hand. Mkono. Samuel. Samuel. Yes. Samuel, I'm not getting
Nilikuwa
you.
nasema usongeshe slide.
Ukifanya nini? Samuel.
Yes, sir. I was saying usongeshe slide kidogo chini ni screenshot na place from the graphs hapo chini.
Your audio is not very clear. You wanted to screenshot? James?
Yeah.
Mwalimu,
Yes.
there was a question where you were deriving the 3 equations in power.
Yes.
The third equation, power is equal to v squared over r. I have not seen how you have derived that.
Oh, I
The third
guess.
equation.
Let me do it. Let me do it now. That you see, that is my work. Let me do it right now. Power equals to v I from v is equal to I R. I is equal to E all over R. So P becomes V, this one, times
Yes.
V all over, which is actually this one. Okay?
Yes. Yes. Yes.
James, tuko sawa?
Niko sawa.
Anybody else? Raise up your hand so that I can see. Raise up your hand. If you have a question, raise up your hand. Put up your hand, please. So are we okay now? We can follow it from the video. You can follow it from the video part. The class has been good. I must thank you for the cooperation. Now I can stop sharing so that I can see you. Good, I can see all of you. Now, the class has been good. I must thank you for the cooperation. Make sure you follow. The learning has been so good. I think by the end of today, my dream, my goal is to send all those videos for all those classes that were there. Make sure you click that link. When you open that YouTube channel, download it, put it in your phone, use it later, use it later, use it later, understand it better. I will also share the notes. And I was asking whoever has KLB in book 3 to hit my inbox. I want him to get some snapshot and ipigie picture some pages and itumie so that we can move on from there. And I wish you all the best, and I wish to end the meeting now.